So we will start our discussion with continuous valued random variable. Whatever we discussed for the discrete valued random variable, we will hold good for this one. But only thing is, because it is continued value, whatever summation that we have been doing for the discrete valued random variable, we will carry on to integration. That is the main difference. Otherwise, the ideas are the same in terms of the way we discuss the probability mass function. Now we will call it as the probability density function. The cumulative distribution function will again be valid for this. We can also define expectation variance and all that. But the only thing is that because it can take a continuum of values over a range, the way we interpret the probability or the density function needs to be given little careful attention. So what we have a sample space here, and we define a random variable x, which map from the sample points to real axis. But it so happens that for when even after the values that it can take need not be fixed or particular values on the real axis. It may range over certain intervals in the real axis. Okay, it can take any given value over certain subsets of the real axis. So then x is called as the continuous valued random. So here, so if this is how we can have the nature of the random variable is. For example, it can be, the random variable can be, for example, you manufacture a product, let us say a scale, okay, and then after that you measure the actual length of the scale. It is supposed to be 1 foot, but it can take any given value around that 1 foot depending upon the manufacturing process. So that will be continuous value. Then if you measure the voltage across diode, okay, even if there is no power source, there may be due to thermal noise, there may be some power voltage that you may be able to measure. Again, that may take values over certain continuous range. So random variables of such nature are called continuous valued random variables. We want to characterize them. Well, first thing is that because its values are going to take the infinite possible values over a range, if you are given a particular value and then asked what is the probability that the random variable x takes the given value x in the interval of the real axis in which it takes, then this cannot be a finite value. If this is finite, because there are infinite possible values it can take, if one of these values is finite, then you will not be able to normalize it to 1, the whole probability. So this will be equal to 0. The probability that the real valued random variable takes a particular value is always 0. Again, the other way of interpreting is, let us say this value can be, okay, you can specify it with arbitrary precision. Okay, then if you tell that it takes a value 2.31567 and something like that, it may take a value, even first of all if you specify it after realization, if you find out the value, again you will specify only with certain number of precision. Then you can always find certain values which are that they will differ by certain positions. So if you take exactly will it take this value means then the probability is 0, because you can always be able to find that it may differ from any arbitrarily specified value, the actual realization. It cannot coincide with infinite precision. That is the reason why we said P of x equal to x is equal to 0. That is all. So we need not this kind of an interpretation, we need a different interpretation. So for that we use, instead of the probability mass function, we use the probability density function. We will use the acronym PDF for that. So what we use for discrete is probability mass function. Because it was concentrated like masses at certain points, we used this term. But now it is distributed. Okay. So we define rather what is called as the density. So if there are certain values, there is a range of values on the x-axis. Okay, x is the values it can take, on which it can take realizations. Then if you draw that probability, which we will refer it as fx of x. This is the notion that we will use. Small f to denote for the probability density function. That the subscript is the random variable denoted in capital letters, and the value that it takes is this, the same symbol in small scales. So that if it takes some value like this one, so if this is the range over which the x can take, let's say a, b, so this is how we will denote fx of x. Then how do we interpret fx of x? The thing is, it's not to be interpreted that if you take a particular value x here and then treat this as the probability of realization of x, because that is 0. So the way we can interpret it is, if you take a small interval, let us say x and x plus delta x, then if you want to find the probability that the realizations lie in this interval, that can be found by summing over all the integrating the probabilities over this range. And if this interval size is very less, and if this density function is a continuous differentiable function, then it cannot change after 2. So it will take a value which will not change much. So that value times the height will give you the probability. So fx of x is nothing but the value that it takes of, that is when the interval size is very small, or the probability that x lies between x and x plus delta x can be found out by multiplying the density function with the interval size. This is how we will interpret the density function. So now we can also define the cumulative distribution function. Before that, we will look at the properties of the density function. One, because it denotes probability, it cannot take negative values even in any given point. So fx of x has to be greater than or equal to 0. But fx of x can take values greater than 1 over a range as long as the integral of f of x over any given interval, which is what we will interpret as probability, is less than or equal to 1. So it can take values more than 1. You will see why it can also happen soon. So that is not a rule, but that is a property. Fx of x can take values more than 1 over a certain interval, provided the probability interpretation that we will soon give is met. thing is that if we have two values a and b, then so a less than b, then probability that x lies in this interval a and b can be found out by integrating the density function between a. Okay, so this is the one. Again, the other way of interpretation is if you integrate fx of x, then what do we do? It's the ordinary Riemann integral. The way we integrate it, we divide it into subintervals and then use the trapezoidal rule. That is, you will find the value of f of x at the middle of the interval, multiply it by the height of the interval, and then, sorry, that is the f of x, multiply it by the delta and sum it over sigma over n intervals, okay, the delta x, where delta x is what? B minus a by n, and you will take the limit n tends to infinity. So this, whatever may be the function fx of x times delta x is what we will find, that is what will convert to the integral. So what we interpret is f of x is the density of the probability at this point. How much is the density? If you want to find the actual mass, what do? You multiply the density by the volume. So in this case, this is a one-dimensional one. So you multiply it by the interval. So it is, that is why we call it as the density. Then cumulative distribution function. Again, we will use the short-time notation CDF. It is defined as probability that x is less than or equal to x. And this can always be defined because we already shown that intervals of the form minus infinity to x will always be present in the Borel field on the real axis. Okay? And the even space has to map to the Borel field. So for every such intervals of this form, there has to be an event in the even space. So such events will map to these subsets of the real axis. So probability of occurrence of those events will be the probability of occurrence of this, of x taking a realization in this interval, and that is what we define as the CDF. So CDF is always defined for a continuous value random variable. So how does it again, how do we denote it? We use it by capital F. Capital F, subscript is the random variable, small x is the value at which we compute the CDF. It's nothing but probability that x lies between minus infinity and x. And that is related to the density function like this. The other way is for CDF, for a continuous valued random variable, which is differentiable and so on, then we can also write it like this. One more thing that we can also do is that can also be written as, this can be written as so you can always find the probability of realization in any interval using just this idiom. Okay, I think this is good enough. These are the main properties of the probability density function and C2. One more thing is that because probability x equal to x is equal to 0, whether at any given time, whether we write it like this, okay, or probability that x less than a, sorry, a less than x less than b, or probability that a less than or equal to x less than b, or probability that a less than or equal to x less than or equal to b, all are one of these two. You don't need to worry too much about this, because probability is, whether it's a closed interval or open interval, will not matter. We have a mixed random variable where in addition to the continuous value there are certain discrete values it can take, then only you have to pay attention. Otherwise you don't need to bother. Now let's look at certain well-known continuous valued random variables that we often use in our engineering scientific application. One is a random variable which has the uniform distribution. In continuous, this is the continuous analog of the discrete. But later on, whenever we say uniform random variable, we only normally mean only continuous uniform random variable. So, because it is a continuous random variable, it can take values over certain subintervals of real axis. It means that those subintervals need not be contiguous. It may be at different non-overlapping places also. But let's not look at those things. You will say that the subinterval is, there is only one interval in the real axis in which the realizations take place. Let's call that this one as A, B, A less than B. There are two values A and B, and the interval is always AB. This is the range of the x. Range of values x can take, the random variable take is this. So we want to characterize this. But by uniform, what it means in the discrete one, you take, there are the discrete values x takes, whichever value, the probability of realization of one value is equal to the probability of realization of any other value. It is the same. They are all equiprobable among all possible values of realization. That is how we define it in the discrete. But here, probability of x equal to any given value x1 is 0. So we cannot say that way of defining uniform random variable. Rather, what you would do is, if you take any interval, two given intervals in this range of values it can take, as long as the size of the interval is same, the probability that x takes a value within this interval is the same as the probability that it takes a value in any other interval as long as the interval size is same. So that is how we define the uniform random variable. So the entire probability is going to be the same. So if you plot fx of x versus x for a uniform random variable with values lying between a and b, it has to be a constant. So immediately we can draw or plot the fx of x. It has to be like this. But only thing that we don't know yet is the height. We know it is has to be constant, and we take only values in this range, which means the probability of realization outside the ranges are also 0. But the height is yet to be found. So how do we first write the effects of x? See, this is the normal way in which we write down the density function, distribution function, and so on. You can give a formula, but the formula may be valid only over certain ranges. So we may split the whole definition of this function over certain ranges, and each range what is the formula that is valid. That is how we write. So it is 0 for x less than or equal to a, 0 for x greater than or equal to b, and between a and b we need to formulate. If you want to be little more, you can also be little. So this is what we want to find. But how do we figure it out? Because we know that the normalization condition has to be obeyed. Is it being written explicitly anywhere? That is, so this is an important one. So again, applying for this one. So you don't know the height, I will call it as the c, a constant c. And we know that because the interval can be split into minus infinity to a plus a to b plus b to plus infinity and so on. These are all zeros. So we know that f of x is a constant. I will call that a constant as c, okay, into dx. So this to be equal to 1. So c into what we get. So we can plug it in this form. So that is the density function of uniform random variable. So meanwhile, Navya, have you passed the assignments of the sheet?
Yes.
Then you will find the CDF. Again, what is this? Fx of x. Dy. So again for this uniform one, we will give a name for this. This is how we will do. We will use a tilde, which means it is defined. X is a random variable that is defined to be uniform between A and B. When we write like that, it has to be understood that X is a random variable and its distribution is given as U means always uniform, and it has only two parameters, the lower limit and the upper limit, okay, of the range in which x can take. So if you give like this, that's all. You don't need to specify anything more. So in the exam, wherever it is, whenever we give like this, we sometimes we give y, x. If we give like that, that's it. You don't need to give any wording like y is exponentially distributed with the parameter lambda, like just like Bernoulli binomial we defined it. This is how we will always use a shorthand notation for definitions of random variable for well-known distributions. Well, so how is it? Minus infinity to x we have to do, but from minus infinity to a it is 0. So is this constant c, which is again what? 1 over b minus c. And what is this one? X between a to x. Sorry. So here I have put y. So this is what we get. So we can write out this fx of x also, and then also plot it. Shall I rub this one and then I will. How do we specify it? For different values of x you have to give. For x less than a, you will integrate from minus infinity to x. Okay, no, not this is x. It's only this. For x less than a, you will integrate from minus infinity to x. But in all those ranges, density function is 0, so the integral will be 0, and therefore this will be 0. And for x greater than or equal to b, you will integrate it from minus infinity to x. That will include the interval a to b in that, integral a to b. Because of the normalization condition which you have looked at, that integral itself will give you 1. Beyond that, from b to x, it is 0. Therefore, you take a value 1 only. And for x between a and b, it is given by x minus a by b. And if you look at the plot, the distribution CD here, so it will be like this. And then if you look at this one, this is a linear curve. So as x increases, this will linearly increase. It will start from 0 at a, because at a, when x is equal to a, this is 0. When x becomes b, it is b minus a by b minus a, it is 1. So it will linearly increase from 0 to 1. This is 1, and then remain constant. So this is how this CDF will look like for a uniform randomization. Is there anything more? Yeah. Any question? Now let's also, having done these two things, we will also go ahead and then derive the two statistical quantities, which is very useful. One is the expectation and there is the variance. So again, for continuous valued random variable, how is it defined? General definition of x into dx. What we did for summation, that is, every value x takes, you give the weightage of the probability that it takes that value and then sum it over. That is how we did it in this case. In this case, you evaluate, you integrate x with the probability density that an interval around that x is taken. That is, x into x is the dx is the interval and fx of x is the probability. So this is the probability of realization in an interval of duration x. That you multiply it by x and integrate. So for this again, it will only become a to b, x will be there, and this is nothing but b minus a dx. So this is the expectation, which is also very obvious because if f takes a value, if this is how it is, the expected value is the middle of these two. This is what you will see. That is, if you say that I will come and visit you between 3 to 4 o'clock, but anytime, equally likely anytime I may come within 3 to 4 o'clock, the expected time of visit will be 3:30, around 3:30. So that is what we mean by this. Then the variance. Yeah. Before I proceed, a small announcement that so coming Monday we will be having our quiz. This is going to be our 4th quiz, right? Yeah, we will be having the quiz. The quiz will be held along with the as per the regular institute quiz. Okay, so you will be given, we will be allocated 2 venues in which 8 to 9 the regular institute quiz timing slots will be held, but you will be writing the 4th quiz for 5 months. That's it. That's the only difference. So henceforth, what we will do is during the quiz timing, quiz week and quiz as per the quiz schedule of the institute, you will be writing quiz, but it will be the corresponding quiz. So I believe this time it is fixed between venues 128 and 127, and this batch and the other batch together will be occupying the same venue. 180 students will be occupying the venue. You will be writing quiz 4 for 5 marks. Professor Andrew students will be writing a bigger quiz for whatever mark that he is going to. So this is how it is. Okay. Huh? Time is 8 to 9 is what is being given by the one, but I will give you a small half an hour window, 8 to 8:30. Okay, I can give a 1 hour quiz if you want. The weightage will be. Okay, or you want like that, I can give a weightage also. If you want, I can increase it also. And then use it appropriately. It's all right, fine. Okay, it will be usual quiz only, 5 marks quiz, half an hour duration. So 8 to 8:30 or so. It will be like that. That is one thing. Another important thing is, because of this 2 holidays that came and then our quiz schedule got disrupted. Now instead of Fridays, we are having it on Mondays. This Monday and the next Monday. So the portion will be for the coming quiz will be whatever I teach till this Friday, and the tutorial sheet will be released by Thursday or Friday. So you will have 1 weekend for going through it. So this is how it is, because the quiz will be on continuous valued random variable. So I am going to devote 3 lectures for that, and my plan is to discuss uniform, exponential and normal, or the Gaussian distribution, and anything else related to it. Maybe I may also discuss functions of random variable, 1 variable function of it, and just to give you an idea so that you can prepare. But now what again the only difference here is we have to find this one E of x, right? That is equal to a to b, b minus a into x will be the, yeah, this is the probability. 1 over b minus a is the probability, this is the x into dx. So no, the x squared, that's what we are finding. But not x, it's not E of x. So x cube by 3, that's what we get. That is b cube minus a cube. Is what we are getting. So b cube minus a cube, we have to, let me rewrite it as b minus a into b square plus a square minus ab by b minus c. And we have also R3. Is this the right way of writing? Splitting it, if you want you can cross check it quickly. So this will be b cube, if you multiply it, plus ba square minus ab square minus ab square minus a cube plus a square. Okay, so ba square, this what is b is b cube plus, and other one is right. Okay, this no. Oh, this is plus. Okay, that's what I. This is plus. Okay. Then it comes. So then what happens? E of x is d plus a by 2. So we can get 4b squared. You take it. So you will have 1b squared and 1a squared minus 2ab. So this is actually ab by 12, which is nothing but b minus a the whole square network. So this is the variance. I also defined one more quantity called coefficient of variance. You will call it, denoted as C for coefficient of x is the random variable. That is defined as sigma by E of x, where sigma is root of variance. So that root of this one, b minus a divided by, this is 3, 4, 2 root 3 into E of x. E of x is a plus b by 2. And therefore we get have you got the sheet?
Yes. So many proxies are there.
Tell me. That's what we want to do. I don't want to do, but anyway I have to do that. What is time now? How much time is left?
8 minutes.
8 minutes. Okay, then switch off this lecture. I don't want